Let's start. So today we are going to talk about adversarial robustness. So let's start with the basic setup that we'll be considering in today's lecture, and also in a couple of future lectures that will talk about adversarial robustness. So recall, in standard ERM, we have a data set with n endpoints, let's say x1 to x1, xi, yi ranges from 1 to n. So this is my data set. And we usually assume xi lives in a d-dimensional space. And let's consider here the binary, the multi-label classification problem with C classes that we have here. All right, so in a standard ERM, we are solving the following optimization. I'm minimizing the average loss on my training set, and I'm picking model parameters theta that achieves the minimum loss. So I'm looking at the expectation of a loss function, f theta and y, and this expectation is over my training set. So I denote that with pxy sub n. So this is basically the formulation that we had before. This is loss, f theta, xi, and yi. Okay, so this is the accuracy or loss on the training set that you're considering. But in the generalization lectures, we argued that at the end of the day, what we care is the accuracy on the test set. But that's basically the goal that we have here. And the idea is that if you are minimizing your error, or you are maximizing your accuracy on training samples, and you're learning a model based on that, hopefully, if the number of samples is sufficient, when you apply it to the test data, when you apply your model to the test data, you're going to have also like a good performance. For instance, on ImageNet, which has about 1,000 classes, there were quite a few successful models in the last couple of years. I can just give you a rough idea. Around 2010, the best performing model, if I look at the classification error rate, in 2010, it was about 28%, around 30%. So this was like the best model on the test set, the classification accuracy. And since then, we have improved. So the classification error, the models, they are trained in a better way. The architectures that we use, they're better. So in fact, we could obtain an error rate of, roughly speaking, 2 to 3% on ImageNet. And just to note that the human classification rate, because if you have humans to classify these samples, they can make some errors. On average, humans, they make about 5% classification error for this data. So it's close to 5%. So in fact, the models that we have, they perform as good, or in some cases better, than how humans would classify these examples. So that's a great result. But is it enough? Are we done? Are we done with ImageNet and with classification? Right, so this is a really good result. So the answer is not so fast. Exactly. So classification error or accuracy on test set is a very important measure. And these results, because of that, they are quite significant. But by no means it is sufficient. So we need to also understand other aspects of the model, especially if you want to deploy them in practice, in real life applications. And one of those aspects is robustness. All right, so robustness has been, studied in different settings, even for classical models like linear regression, PCA, or some other classical learning methods. And there are different views, that you can think about robustness. You can think about robustness to, natural variations in your data, right? So if you have some, images, maybe the lighting is going to be different in the test time. Maybe the backgrounds of the images can be different in the test time. So these are somehow natural variations that could happen in the test time. And that's one way to think about robustness. And we'll be talking about that kind of robustness, which is distributional robustness or robustness to other domains in some of the lectures during the course. But today, we are going to focus on one specific type of robustness called adversarial robustness. All right, so what is an adversarial example or an adversarial attack? Let's say you have a good classifier on ImageNet, and it classifies your images pretty accurately. Let's say we have a cat image. So I'm gonna do my best to draw a decent cat. Okay, not bad. So this is my input, X, and my classifier classifies this correctly as a cat. So that's good, and that's what we were hoping to get from our classifier. But we have realized that if you perturb this image just slightly, you add like a little bit of a noise to it, I'll call it delta, very small amount of noise, you would still get like an image that will look like a cat. Same image, but you may have like small, really small noise in your image. And even you can make this delta very small that this noise is imperceptible. So you don't actually, humans won't be able to tell the difference between X and X prime. But you can design your delta, your perturbation vector, in a way that now my model is going to predict a different label for this image. So my model is going to predict, for instance, a dog label for this image. And that is not good, right? Because this is still the same image. It's for humans, it is still a cat, but you make these really imperceptible changes and it can flip the label from model's prediction. So this delta perturbation vector that we have, we call it adversarial perturbation vector or noise vector. And X prime that we have here, we call adversarial example for a given X. Okay, so let me see, there are some questions. Does it depend on the amount of noise? Yes. I'll talk, what are the noise models that, that we will consider and we consider. So here, just roughly speaking, the noise is small, it's kind of a perturbation of your image that is imperceptible. So Meg, yes, go ahead.
Professor, like, how do we define what is the same for human? Like, when does it stop being the same?
That's a good point. So I'll answer that. Hold on to that question. So I'll address that directly. Next. Okay, so that's a good point. In fact, let's step back and ask this question: that what is an adversarial example? So, all right. So what is an adversarial example? All right, so we say X prime is an adversarial example for X given under a model, let's say F theta of X. So my model is trained, theta is the model parameter, X is my input. I'm gonna say X prime is an adversarial example if two conditions are satisfied. One is, obviously, I want my model to have different predictions for X and X prime. So F theta of X should be different than F theta of X prime. So in other words, my model predicts different labels for X and X prime. So that's the first thing. But the second condition is, because, here I'm not, putting any constraints on X prime. So if you even completely change your image, then that will satisfy the first condition. Your model is going to have a different, prediction for X and X prime. So the second condition that we have here is humans acting as a classifier would classify X and X prime the same way. So I'm perturbing X. From a human point of view, it is that the label of X is unchanged. If it was a cat, it is still a cat. But my model, from my model's point of view, my label, the label that my model is going to predict, is going to change. So that's the formal definition, in a way, of adversarial example. But as your friend mentioned, what is this part, right? So even in the definition of adversarial example, we have this constraint that we want to find X primes such that the true label of that example is not changed under the perturbation. But the key challenge is that we don't have a precise mathematical function or definition of human perception. So that's one of the main challenges that we have here. So if we had that function, then we wouldn't have this problem, and perhaps we could have used that in the classification itself. So the whole goal is to use this neural network to do the classification for us. But here now we have an optimization we have a definition such that one of the constraints depends on the human perception. Right? So we don't want to have a label, the true label of X prime, to be different than X from a human point of view. So that's one of the key challenges in adversarial robustness in general. All right, so just to give you a different perspective, for a given X, and for a given model, consider the set of all X primes such that human would basically have the same label for X and X prime. So suppose this is the set of all examples X primes such that humans have the same label. So this is basically the set of unrestricted adversarial examples for that particular X for a given model. And obviously we are assuming the label is going to be fillet, right, under the model. All right, so a subset of this bigger set that we consider is the set of imperceptible adversarial examples. imperceptible adversarial examples. And from like the naming, it is obvious these are examples X primes such that not only human has the same label for X and X prime, but humans, a typical human, could not even tell the difference between X and X prime. So it's a little bit of a stronger assumption here. So the change that we are making in X prime is imperceptible, right? So if you want to write a mathematical definition, you would look at X primes such that maybe like the true perceptual distance between X and X prime is less than a particular threshold, that basically threshold causes the change between X and X prime to be imperceptible. All right, just to give you some examples to have this in mind, because sometimes in papers they have more restricted definitions of adversarial examples. It's good to have like this big picture in mind. Let's say I have a stop sign, maybe with the red stop sign. That's my X. Now I'm going to create an adversarial example by adding an adversarial patch to it. Let's say I have a patch. It's like an adversarial patch. So I'm perturbing X using this patch, but humans can tell the difference. If I show X and X prime to a typical human, if we say, okay, so yeah, I can see there's like a patch added here. So the change is not perceptible. It is not imperceptible. So the change is perceptible. But nevertheless, humans would classify X and X prime the same way. Both of them, they are stop signs. So X prime is an adversarial example, but it lives outside of the set of imperceptible adversarial examples. So contrast that with the example that we started the lecture with, that we had a cat. I'm really getting good at drawing cats. And then your X prime is also basically the same cat with very, very small imperceptible changes, maybe one or some, little amount of changes that we are making. And humans would not tell the difference between X and X prime. And obviously it is a stronger condition. And because the humans won't be able to tell the difference, then the label of X and X prime, the true label of them, will be preserved. Okay. But even this set, this more restricted set that we have, the set of imperceptible adversarial examples, it kind of depends on a notion of human perception. So here we are saying that humans can tell the difference between X and X prime. So again, that is another difficulty that we have. So in one of the lectures, I'm going to talk about this function, the function that can approximate perhaps the human perception later on. But one way to think about this problem, and that's how we are going to start the adversarial robustness lectures, is to consider specific threat models within this imperceptible adversarial example set. Now, for instance, I can look at, let's say, a smaller subset of imperceptible adversarial examples where I'm bounding LP norm of my my perturbation noise. Or you can have some other constraints for your perturbation noise in order to make sure that the difference between X and X prime is sufficiently small and humans won't be able to detect such changes in your X and X prime. All right, so that brings us to the idea of threat models. So we basically, it's very simple. So we are going to assume X prime is within a threat model of X with a budget of epsilon. For example, the most probably studied threat model is the LP model, where we are looking at X primes such that the LP norm between the difference of X and X prime is bounded by epsilon. So you can look at examples of it. You can look at L infinity, L1, L2, and even some other related threat models like L0, which is not a norm, but still, you know, it's an interesting threat model. L0, which basically changes few number of pixels in the image to create an adversarial example. So these are basically LP threat models, right? So that's one perhaps small subset of the whole imperceptible adversarial example. But you can also think about non-LP threat models. For instance, if you give me an image, let's say this is the image of one sample from MNIST, like a 2, if I do like a small translation or rotation of this image, I'm gonna get an image like this 2. Remember the previous location of my 2, let's say it was something like this. So it was 2. So I basically translated or rotated my digit slightly. So if you think about this, if you compute the LP, so this is X prime, this is X. If you compute, let's say L2 or L infinity between X and X prime, this is going to be a really large number, right? Because every pixel is changed quite significantly. So the LP is going to be large. So that means that this example, X prime, is not in the set of LPs. So from an LP point of view, the norm difference between X and X prime is a large number. So we are not in this set. But still, the change is imperceptible, right? You just like maybe with 1 pixel, you rotated or translated X to X prime. So therefore, we are still in the imperceptible set, but perhaps not in the LP threat model. So there are a lot of interesting non-LP threat models. I'll just give you one example. So one threat model is defined based on optimal transport or Wasserstein. So we are going to talk about optimal transport and Wasserstein measures in lectures that will talk about generative models. But roughly speaking, a Wasserstein or an optimal transport measure measures the cost of a transportation between 2 distributions. And here, if you normalize your images to represent distributions, then in the example that we just mentioned, the transportation, because the translation is very small, it's gonna cost really a small amount. And therefore, if you look at the Wasserstein between the normalized X and X prime, it's going to be a small number. So that threat model can be defined as all X primes such that perhaps the Wasserstein distance between X and X prime is less than epsilon. So I'll talk about this Wasserstein distance. I don't want to go into the details of it at this point. I'll talk about it, later on in Gan's lecture. All right, so that can be another threat model that we have here. Let's say that's the Wasserstein threat model, but you can have some other threat models. Sometimes they will be overlapping, sometimes they will be non-overlapping. And I want to emphasize, and I'm going to discuss this later on, that we may if we consider all of these threat models, there may be some examples that are imperceptible and not covered in any of these threat models, the union of these threat models. Okay, so that's something that we'll be discussing later on. Okay, so that's about the formulation of this problem, right? So now we understand what adversarial examples are. And next we are going to basically talk about two problems of attacks and defenses. So basically that was formulation. Next we are going to talk about attacks. And after that we are going to talk about defenses, right? So this is done. And this is what we are going to do next. All right, so I see a few questions. Let me pause and see what are the questions. Yeah, here we are making a separation between misclassification error and adversarial example, right? So X is not misclassified. So here X is correctly classified, but X prime, the label is going to be different than the label that we have for X. All right, so there are some questions about the attacks, but we haven't talked about it yet. Is translation also considered as noise? Yes, but it is not an additive noise, right? So we are not just adding a pixel, adding some noise to each pixel. So we are translating it. That's why it is called non-LP. Okay, so I think I covered, I think most of the questions. All right, so let's talk about the attack problem. All right, so what is the goal in the attack problem? So here we are given a classifier and we are given an input, given X and given a classifier. So I want to compute an adversarial example, X prime, such that the label that I'm predicting for X, the true label, let's call it with C star, is different than the label I'm predicting on X prime. And let's say I'm looking at the LP threat models and I want my X prime to be within an epsilon LP ball around my X. So that's my goal in the attack problem. So that's one way of thinking about the attack. So I'll talk about another way of thinking about the attack problem later on, but that's one way to think about the attack problem. All right, so there are different variations of attack problems. So I'm going to, in a high level, explain what is out there and what are the formulations that people they look into, and place the formulation that we are going to consider in this lecture in that picture. So one way to think about attacks is either to have targeted or untargeted attacks. Targeted or untargeted. So in the targeted attack, because the name is very explanatory itself, we are picking a particular target label, and I wanna create X prime such that my model predicts that particular label that we are targeting. So you are given a target label, let's say T. So obviously this T is going to be different than the true label that I have, C star. Otherwise it won't be an adversarial example. And then I'm going to ask my model to create X prime such that the label that I'm predicting for X prime is that target, T. So, but the idea here is that we are picking the target. And how can we pick the target? There are different ways that people they have looked into. One is you can randomly select the target. You select the target, from some other labels that you have, and then you ask your model to create an example to predict that target. You can look at all of the possible targets all labels that is not equal to C star and either pick the best or the worst target, the easiest and the hardest target to understand the robustness of your model. But that's basically the idea of the targeted attack. In the untargeted attack, T is not given. Right? So we are just asking the model to just flip the label. It doesn't matter which label we are flipping to, just flip the label to something. So it is easier in terms of attacking, right? Because we are not, forcing the model to go to a specific wrong target. We are just saying that, okay, just flip the label. Right? So in practice, it is important to understand the robustness of the models against targeted and the strengths of the attacks, for targeted problems, because, sometimes you may have two labels that are kind of, similar to each other. Like on ImageNet, if you have looked into the labels of the ImageNet, you see there are a lot of dog classes. And even as a human, I can't sometimes tell the difference between the two types of dogs, right? So in that case, you may not get a true sense of security, true sense of robustness if you're just doing the untargeted adversary, or if you're just thinking about untargeted adversarial robustness. So most of the times we are going to focus on the targeted attacks. Okay. All right. So another classification of the attacks is based on how much information adversary has access to. So we have white box attack and we have black box attacks. In the white box attacks, here adversary basically knows everything about the model, about the parameters of the model, about the defense. Adversary basically knows everything. So what is the model architecture? What are the parameters? Everything. So it is basically a really white box, the model to the adversary. In the black box attack, we are restricting the knowledge of the adversary with respect to the model that we are using in our classification, has limited knowledge about the model, but it can access the model input output. So it can query some inputs, the model on inputs to observe outputs. It can say, okay, what happens, what is my output if I have this input end to end, but the adversary doesn't know what is going on in the black box that we represent as our model. And between these two extremes, there are some other types of attacks that the adversary perhaps has some partial knowledge about the model. Maybe it knows the model architecture, but doesn't know like the parameters of the model. So those are called gray box attacks. So in the lectures, we'll mainly focus on the white box attack. So we are going to assume adversary knows everything, because that will give us a little bit of a fundamental perspective about the robustness of the model. So here we are not restricting the adversary's power. We are saying that if adversary knows everything, what would happen in terms of our classification accuracy. All right, so the final classification of these attacks is based on the types of attacks that we'll be considering. One is inference time or evasion attack. Which is basically the attacks that I motivated the problem with. So you give me in the inference time, you have already trained your model, right? So your model parameters is fixed. You give me an X, you give me an example, and I want to find X prime to change the label to some incorrect labels. Right? So that's basically the inference time evasion attacks. But you can think about the attacks during the training. So that's called training time or poison attacks. So in today's lecture, we are focusing on inference time attacks. And in one of the lectures, I'll talk about poison or training time attacks as well. But today we are going to focus on inference time attacks. All right. Let me pause and see if there are any questions. Is this clear? The types of attacks that are out there and the types of attacks that we are considering. Tasneem, go ahead.
Yeah, is it possible to make repeated queries and make some decision about the model architecture? Will it be then transferred to gray box to white box?
Right. So in black box attack, so you can basically, there are different ways to do it. You can have model replacement. You have like different queries, and then you maybe train your own model. But even better, because a lot of adversarial examples can transfer from one model to another model. You can create an adversarial example, let's say from a ResNet, and then apply to the black box model, and oftentimes that is successful. So because of that, one of the reasons that we'll be mainly focusing on the white box attack is that we can get around the black boxness of the attack by some of these techniques, and it has been shown that usually those types of attacks are pretty successful. So that's why we are basically assuming adversary knows everything.
Okay, thank you.
Sure. Okay, so let me move on. All right, so what is the attack optimization problem? In the attack optimization, so remember during the training of the model, we are minimizing the classification loss, right? So that's basically the goal. But in the attack, we are gonna do the opposite. We are going to pick like a perturbation delta that maximizes the classification loss. So we wanna pick a delta that maximizes some sort of a surrogate function for the classification loss when we are looking at X prime and the label that we have Y, which I think I call it C star as well. But we have a constraint, let's say in LP attacks, that the LP norm between X and X prime is less or equal to, let's say, a small number, epsilon. All right, so for this function, for the classification loss, again, you can use cross entropy, or you can use other surrogate loss functions. For instance, this really nice paper by Carlini and Wagner, they propose like 7 different loss functions that you can use based on the difference of the logits, different types of functions that you can think about, maximizing them in order to create an adversarial example. Yeah, so you can basically formulate this as both targeted and untargeted, depending on the loss function that you define. For instance, I can define this loss function to push my the targeted logit to become the highest compared to the other logits, and that will be a targeted attack. Or you can think about picking a loss function that just like maximize the logit or the probability of any of the other classes that we have. So that will be an untargeted attack. So depending on the loss function that you choose, you can frame this optimization as targeted or untargeted attacks. Okay, but either way, so the question is how to solve this optimization problem. All right, so as before, the objective is non-convex, but non-convex minimization or non-concave maximization. But I hope that we are no longer afraid of non-convexity, right? So we have like this gradient descent or stochastic gradient descent that we use for training the model. Perhaps we can use gradient descent to basically deal with this non-convexity. But here we have a constraint as well, right? So we need to make sure that when we are doing our updates, we are not outside of the feasible region for X prime as well. So to deal with this optimization, one of the first methods that were developed called fast gradient sign method. Or it is called FGSM attack. It is mainly developed for L infinity, MPZ L infinity. So basically the threat model is L infinity. And the idea is really, really simple. It is just one step of local search. So here I want to find the delta that maximizes this classification loss, right? So remember before, when we are minimizing, we are going in the opposite direction of the gradient. So I'm just gonna look at the gradient direction and I'm gonna go in the direction of my gradient. But how much I can go, I'll go until I basically violate. I don't wanna violate my constraint. So that's basically the delta that I'm going to compute. I would call it delta FGSM. So I compute the gradient of my loss, say F theta X and Y, and I'm gonna find the delta that is basically in the direction of my gradient. So I wanna maximize the inner product between the direction I go and the direction of my gradient. So the only constraint that I have here is that, let's say my L infinity norm is less or equal to epsilon. So I don't want to violate my L infinity constraint. All right, so that's basically just one local update that we have here. But this maximization is actually really simple, because if you think about the L infinity norm, it is basically applied component wise on the delta. So what you need to, and the perturbation budget is epsilon. So what you need to just look at the sign of your gradient in that component and go by epsilon in either positive direction or the negative direction of the sign, because the L infinity is applied component wise. So for L infinity, this is in fact really simple. So it is just epsilon times the sign of your gradient. And that's why the method is called the fast gradient sign method. It is developed specifically for the L infinity attack, but you can actually do it for other attacks as well, because this optimization is quite simple. You can do it for L2, L1. You won't get the sign, but you'll get like some simple solution. For L2, it will be basically the normalization of your gradient and then multiplied by the budget that you have. And you can, do basically similar computations for L1 as well. Yeah, that's basically just one step of, this is a one-step attack that we have here. But it's really fast. So you just like need to compute your gradient, look at the sign, multiply by epsilon, add that to your X, and hopefully that will break your from an attack point of view, hopefully that will break your system. All right, so there are some questions. Let me see. All right, it's great that people are you're answering each other's questions. That's really good. All right, good. So you can think about, an extension of this method, which is multiple step. It is like an iterative attack, because here we are just computing the gradient at that point, going one step, so it may not be really effective. So one way to extend this attack is based on an iterative attack called projected gradient descent, or PGD. So PGD is basically an iterative version of the FGSM attack. All right, so the idea is that I'm going to apply FGSM attack in a repeated fashion, but I also want to make sure that we are satisfying the constraints, right? So we are not going out of the constraint set that we have, and we are going to, after each application of FGSM, we are going to project or sample that we are computing to the feasible set that we have. So that's why it is called projected gradient descent. So the algorithm is in fact really simple. So you start, let's say at iteration 0, you start from your input. And let's say at iteration t, you have xt as your candidate adversarial example, and you're just gonna do like a one-step FGSM attack. Let's say you just add eta times g of t, where this g of t comes from FGSM. So this g of t is, again, in the FGSM, we had max over delta. We look at the gradient of the loss. So we compute this FGSM step. We just add that to our X. This is our candidate adversarial example that we are updating in this iteration. I'll just call that X tilde t plus 1. But when we are adding, based on this step size that we have, we may violate the constraint that X tilde, the adversarial example, it should be within an epsilon ball of my X. So what I'm gonna do next, I'm going to project. So there will be a projection. And I'm going to look at xt plus 1 to be the projection of x tilde t plus 1. This projection is over for our example that we are looking at LP. So we want to make sure that xt plus 1 minus my input x, the norm is less or equal to epsilon, right? So that's basically the projection. For L infinity, for instance, this projection is really simple, right? Even for other LPs, this projection is very simple. So for L infinity, this update is basically, I'm looking at xt plus 1, I'm looking at clipping between x minus epsilon and x plus epsilon, right? Because I don't want each of my pixels to be perturbed more than epsilon. So I'll just clip, let's say this x tilde that I compute with my input, which is x0 minus epsilon and x0 plus epsilon. I'll just clip between these two numbers. For L2, you just normalize. And that's basically the projection step, and then you iterate. You iterate for a few times, and you compute your attack. All right, so roughly speaking, comparing these two attacks, oftentimes PGD is more effective than FGSM attack, right? Obviously, because we are using more iteration, so it is more powerful. But there are some recent papers that they show that you can, in fact, by adjusting the learning rates and properly adjusting tuning hyperparameters, you can also have a really good FGSM attack, one-step attack, against your model. But usually PGD is one of the standard attack methods that we use in practice. All right, so that's basically about attack methods. Let me pause and see what questions we have. right? So all of them, there are, I think there are some questions about, targeted and untargeted attacks. Depending on the loss function that you have, all of these techniques can be used for either of them, right? So in the targeted, you are just, for instance, maximizing a particular, logit or probability. In untargeted, you basically don't care about that particular probability, and you want to say any of my, incorrect labels. If you pick, that's fine. So it basically integrated in the loss function. Yes, these are all white box attacks. Yeah, so there are some, rules to pick the step size. Usually you don't want to have a large step size. Even in the convex case, if your step size is large, you won't converge. So there are some basically bounds on the step size, but oftentimes we use a small step size. All right, so let me move on. I was more optimistic about how much I can cover today, but let's at least finish the attack part. All right, so far the attack problem, in the attack problem, we assume the budget is given. The attack budget is fixed. So that's the assumption that we have. We are saying, okay, I give you this budget epsilon, go find me an adversarial example. But we can also think about this problem from an related but an alternative point of view, that we want to find the closest adversarial example to my input. So I don't know what the budget is. Maybe for some inputs, my budget is, the budget I need is going to be larger, the attack budget that we need compared to some other inputs. So maybe, perhaps a better formulation or an alternative formulation would be the following, that we want to find closest adversarial example to our input. So in that case, our optimization basically simplifies to, I want to find the minimum perturbation, let's say within an LP threat model, such that my model, when I'm perturbing my X, is going to produce a, targeted, label T, which is not equal to the true label that I have. And I want, of course, my X plus delta to be a valid image. Pixels are normalized between 0 and 1, so these are often called box constraints. All right, so this optimization is very related to the previous optimization that we discussed. Here we have, again, some constraints. Our objective is convex, but our constraints are non-convex. So the previous optimization was the other way around, right? So the objective was non-convex, or constraints, they were convex. So one way to deal with this optimization is to bring the constraints to the objective using Lagrange multipliers. And then we'll have an unconstrained optimization, and then we can apply gradient descent in order to approximately solve it. So Lagrange multipliers, or Lagrange dual form, if we write, so we'll get an optimization like we are minimizing, again, delta minus lambda, like perhaps a classification loss that I'm considering, f theta x plus delta, and the true label that I have. And of course, I need to have my box constraints. So this can be satisfied by clipping. So that's easy. And now my objective has basically a non-convex form, but I'm going to use gradient descent in order to approximately solve this optimization problem. Right, so the idea here is that I'm minimizing this term. So I'm basically trying to find closest adversarial example, but you see, like I put the negative here, so I'm maximizing my classification loss. So I want X prime that I compute to misclassify, but the delta that I'm going to compute, I want to be as small as possible. And this lambda kind of, controls this trade-off. Right? So you may want to, if your lambda is very large, then you are putting a lot of emphasis on just finding an adversarial example. But you don't care if that example is close. But if your lambda is small, then you basically start with like a smaller radius and see if you can find an adversarial example or not. So one way that was introduced in Carlini and Wegner's paper is to have like an adaptive grid search for lambda. Maybe start with a small lambda, and then if you couldn't find it, increase the lambda, and see if you could find adversarial examples within that budget. Otherwise, keep doing that. All right, so that was basically what I had in mind to talk about the attack problems, right? So we talked about, different, formulations of the attack, either, for a fixed budget, or if you want to find the closest adversarial example, and we looked into FGSM and PGD attacks. So that was basically covering the formulation and attacks. And next we want to talk about defenses, right? So here in the attack, we assume the model is fixed, but now we want to say, how can we train our model to enjoy robustness against attacks, right? We don't want to be vulnerable against attacks in the inference time. All right, so let me pause here and take some questions. All right, so one question is, how do we define closest? Right, so it depends on your threat model, right? So in the LP threat model, I'm looking at the LP distance between X and X prime, and that's my objective. But you can look at, think about other metrics to define your closeness in this space. All right, so in the defenses, okay, so thinking about ERM, so what did we have in the ERM, in the standard ERM? So basically, we are picking model parameters, minimizing the loss over my training set. Classification loss over training set. So this is XY. I'll just write training. And we know, like, the model, if we train based on ERM, is going to be very fragile against adversarial attacks. So we want to robustify the model during the training. So one way to do that is via adversarial training. So the idea of adversarial training is quite simple. So instead of looking at just the classification loss on my training set, I'm going to, for training samples that I have, XY in my training, I'm going to find the worst perturbation for each of them, and I'm going to minimize my error on the worst perturbation. So I'm going to find X prime that maximizes this classification loss that I have, theta, X and Y. And of course, X prime perhaps has a small perturbation norm compared to X. So instead of minimizing the classification error, I'm looking at the worst perturbations of my training samples, and I'm minimizing my error over those worst perturbations of my training samples. Yes, thank you. So there's an X prime here. All right. So then the question, again, we have this optimization problem. The question is how to solve it. This is a min-max problem, and we are going to spend one lecture, hopefully, during this course, just to talk about, you know, complexity of the min-max problem. So here we have a minimization, we have a maximization. So, but practically speaking, the way that we solve this problem is, first we solve the maximization problem. The maximization problem is basically the attack problem that we discussed. Right? So I'm finding X prime that basically pushes my model to be wrong. So the inner maximization problem is basically the attack problem. And you can use, for instance, PGD or FGSM in order to approximately solve for X prime. So the outer minimization problem, I can just use gradient descent to solve it. So I compute my worst perturbations, and then the gradient of my model with respect to theta is going to be the gradient of the objective evaluated at those worst perturbations. And that's basically it. So we'll solve this using alternating between PGD and gradient descent. So that is adversarial training. But there are a lot of other heuristic methods to defend the model. So I'm going to perhaps next lecture talk about some perhaps false security hopes that we sometimes get by using some heuristic defenses. But then I'm going to also like explain, you know, how we can break those defenses using iterative models, and talk about perhaps, you know, we need to think a little bit about this problem from a more fundamental point of view. You know, can we even argue that we'll always have adversarial examples, you know, under some conditions? And if not, are there some provable defenses to robustify models against these types of adversarial attacks?